welcome everybody. This is great. We're going to talk about quantum computing. And since I am a venture capitalist, I know very little about it, and we're going to ask a true expert here, Christian Weedbrook, who runs Xanadu, and I'm an investor in Xanadu, and we were blown away by their technology. We had been investing in quantum computing for quite a while with D-Wave and with Rigetti. And then when we met Christian, we thought, oh, well, this might change everything. And we're very excited about what it could do. So Christian, maybe you can start with just, how does it work?
For sure. Thank you, Tim. And I remember the time when we first met. You were in Toronto, I think at Collision, and you came by and we kind of wowed you with our photonic-based approach, which is one of the unique approaches to quantum computing. But essentially, you know, the quantum computer, it's still a computer, but it's something that can do you know, certain applications, key applications, much faster than what you can do with traditional compute. So it really goes head-to-head with traditional supercompute. So it tackles problems that would, let's say, take you know, a year, 2 years, or whatever, and you can take it down to a few seconds or a few minutes. It's that sort of powerful. The other type of problems it can solve is examples of problems that would have taken, even if you ran the world's fastest supercomputer thousands of years, it would take a long time to solve the problem. And so these examples would be in drug discovery.
But you said what you were doing. You were working on optical quantum computing. And I thought that was a good approach.
We still are.
Oh, okay.
Yeah,
what else are you doing? What has changed?
Yeah, so the key thing for us is really, it's all about now 1 million qubits. And it's about building a quantum data center that can actually solve these problems that we were talking about. So another way to think about 1 million qubits is fault tolerance and error correction and all these sorts of things. Very hard problems to solve. But once you can solve that, you'll have a small to medium-sized data center that can now start solving these problems. And, you know, better materials for batteries, which we work on, new candidates for drugs, AI, machine learning, all these sorts of things that really would take a long time to actually get. So give you an example.
So you're doing more of the peripheral work around quantum computing. Why? I mean, by the way, every great company that I ever backed pivoted at one time or another, just so you get the idea. But so did the optical quantum computing work, or did you run into problems, or what made you, or was the opportunity, did the opportunity just present itself that, hey, we want to be around the periphery of this?
Yeah, so we still, the algorithms and application, that's still a focus, and fundamentally we're still a hardware company, so we are looking to build a quantum computer. When you invested, what we are looking at is sort of the, what can you do without error correction and fault tolerance? We passed through that along with other companies, and now we're looking at error correction and fault tolerance. So still building this quantum computer. But the reality is a quantum computer of this magnitude will take up half a football field. So, you know, the quantum computers we have now, Xanadu and others, you can access them over the cloud. But the end goal is really to build all this infrastructure. And in fact, you'll have, say, 5,000 server racks in a quantum computer. They'll be all networked, very much like a traditional data center. But in each side of these, inside of these server racks, you'll have your approach. So for us, we'll have photonics. And that's, one of the great benefits about photonics is the ability to network the individual server racks. Networking is really one of the key aspects for scalability, no matter really what approach that you do.
So everybody is familiar with Moore's Law, where $1,000 worth of compute power doubles every 18 months. Moore's Law has gone on a pretty good, consistent curve. It seemed to be kind of flattening out, and then quantum computing. Give everybody sort of a sense for the difference between the processing power of $1,000 worth of CMOS compute power and $1,000 worth of quantum computing.
Yeah, maybe the best way to explain, at least the way I think about it, is Xanadu demonstrated quantum supremacy. So essentially you choose a well-defined, in this case, a math problem. So it's not a business problem yet, but it's an important stepping stone. And this particular math problem would have taken, using the world's largest supercomputer, which I believe is in Japan, called Fugaku, if you'd had used all 7.2 million cores, simultaneously, it would have taken 7 million years to solve this problem. Our computer, called Borealis, photonic-based one, took 2 minutes to solve the same problem. So that's the sort of craziness. Now what us and others in the industry are
all
doing,
these big computers, they have names? Is this like ships? You have to
yeah, I think so. I think so.
Name your ship, but usually those are female names.
Yes, Borealis. I don't know really what gender it is, but
Were you looking up at the sky at night in the
yes,
winter?
yeah. You know the northern lights and obviously
Right.
the lights and photonics.
So if you're building a quantum computer that is going to be that much faster at that specific use, how many years are we looking at in where we're using quantum computing devices all the way across all applications, so that we're using them for faster neural networks, we're using them for better deep fakes, we're using them for supply chain management, for drug design, for what else? What do they call it when you're figuring out how water runs?
All right, fluid dynamics.
Fluid dynamics.
Yes, yeah. So the current thinking by us and others in the industry is that the lowest hanging fruit this decade will be for very big problems, but a subset of problems. So drug discovery, material design, so in terms of quantum chemistry.
So it's going to be good at running many iterations of something. So the way people think about drug discovery now is they do most of it on the computer.
Yeah.
And they run simulations of drugs and diseases, and they try to find a match. And they do it over and over and over and over. And that's the kind of thing quantum computing is really good for.
Yeah.
If you're running a program through many, many times very quickly.
Yeah, for instance, you mentioned drug discovery. The usual stats is taking a drug to market, takes 10, 12 years, billions of dollars, but then 80% of them fail, the most promising candidates. So a lot of time and money goes into that. And as you mentioned, the very starting point is the chemists, pharmaceutical scientists actually using computers to simulate. Now the possibility, the combination of all possible drugs you can kind of come up with is endless. So they need to narrow that down. They use computers, they use past results, they use data, they use heuristics and their experience, but it's still, as we saw, 80%, 10 years and billions of dollars are wasted. Quantum computer, because these candidates are inherently quantum mechanical, the belief in quantum computing community is you can use a quantum computer that's fully controllable, a quantum system that can mimic what's the system that you're concerned with. So therefore, you can actually get better candidates. So you're really not wasting 80% of your effort and all your money and time. And the same applies to what we work on, which is next generation battery development as well.
So there's a thing that I still have trouble getting my head around, and maybe you can kind of explain it, that quantum computing runs, in effect, a simulation where it has two states at once, and those states can be both on, off, or both on and off, and there's a probabilistic assessment, and if you run it through there enough times, you can get 99.9999 whatever probability of it being correct. Can you take everybody through sort of what that's about, and then after you've done that, tell everybody how you got into it?
Yeah, for sure. So as you mentioned, normal computing, digital computing, you have as an input a stream of bits, 0 or 1. You process them through gates, and you have the output, your answer to what you were doing. A quantum computer, as you said, it can be 0, 1, 2, but the interesting aspect is when you have some combination of 0 plus another combination of 1. So in effect, both things happening simultaneously. Now, if you've got just a 0 or 1, so one bit of information, it doesn't really do much. You can do both, but it's when it scales up. So it scales exponentially 2 to the n. So for instance, when you have 2 to the 3, that's 8, you have 8 bits. You have 8 combinations. So you have 0, 0, 0, all the way down to 1, 1, 1. You've got 8 possibilities. Classically, you can just have them in particular order, but not simultaneously. A quantum computer can actually have the superposition or the addition of 0, 0, 0, 0, 0 plus 0, 0, 1 all the way up to it. So now you've got this parallelism in quantum computing. Now the catch though is it really depends on the algorithms that you use, because at the end you can only extract classical bits of information. It collapses this superposition or combination. But there's clever algorithms out there that can kind of, through the quantum parallelism, actually benefit and create these speed ups. And so for me, hearing about that, I, along with others at Xanadu and throughout the industry, a lot of us came from academia. So I was from Australia originally and did a PhD in photonic quantum computing. But before that, I heard about you could do these secret codes, unconditional security using light. And I got into quantum optics and light, understanding light from a physics point of view. And then as you were mentioning about 0 and 1, you can actually encode bits of information onto certain substrates. So what we do is we take the 0 and 1 and encode it on, say, the polarization of a light field. So you need, the famous thing is information is physical. So you actually need some physical medium to be able to carry that 0 or 1. And so for us, we use light.
And do you run into the same problems they do that the ones who use
superconducting, yeah.
Superconductors? Are they, do you run into this? They, well, I guess you take advantage of that thing where they kind of run parallel and they run too close together?
Yeah, so for us, yeah.
What's that called?
That leads to interference that they don't want, basically.
Right.
So,
but then you can take advantage of it and use the interference, right?
Yeah, one of the things, there's nothing to do with quantum, but you hear about, dropping two pebbles in a pond.
Right.
You see the ripple effects, and they both sort of spread out. Some parts of the waves, once they overlap, have constructive interference, so the amplitude increases. Others, destructive, which cancels out the effect. So, our quantum algorithms roughly work in being able to identify the correct solution and amplifying that, and essentially de-amplifying through constructive interference, removing the wrong answers to things. And that's how we try to take advantage of these effects like interference, superposition, and entanglement's another big one as well, where we try to leverage all three to really give an answer that you want that's reliable, but also that is to a problem that classical computers can't do in any reasonable amount of time.
So I'm a Bitcoin holder, and people in quantum computing are saying they can crack the code. Now, it hasn't been cracked to date, so we're happy about that. What do you think the future is there? Is the blockchain just going to blow up, or are people coming up with good solutions so that it never does?
The latter, which is good. So quantum computing really took off in 1994 because Peter showed that if you had a powerful enough quantum computer, you could actually break things that the internet security leverages for its security, like RSA and elliptic curve. And blockchain, I believe, uses elliptic curve for authentication and things of that nature. So what people can do now, there's a strategy, nation states and really any government around the world is downloading now and decrypting later. So a quantum computer needs to be very, very powerful to actually solve this. We talked about 1 million qubits. You're going to probably need 20 million or more qubits. So the reality when a quantum computer of that size will start posing a threat will be in the 2030s or beyond. But the problem is now there's certain things that have a long duration of security. So medical records technically need to last for as long as a human, say 80 years on average. IP, government secrets, all these things people can download now, but they can't decrypt it now because we don't have a powerful enough quantum computer. Now, when it comes to blockchain and other ones, there are other companies, not Xanadu, but ones in the security business, that are actually coming up with better codes, mathematical codes, that a quantum computer kind of looks at and like, we can't crack this at all. Oh. And so companies now are coming, and so there's a replacement.
So we can hold on to our Bitcoin.
You can, yes, okay. Yes. And I'm not going to tell you when we crack it either.
So now if you're building these computers and is it mostly research facilities still that are your customers, or I mean, are there some interesting applications in defense, for instance? Are there interesting applications? Are drug companies starting to buy these to do some drug development? So who are your customers and what are they doing with them?
Yeah, it's really the customers and the interest in customers is really proportional to where we are in the development of the hardware. So where we are now is really about early adopter phase of technology. So for us and others in the industry, governments around the world are very interested, national labs in the US and Canada, large multinational corporations, ones that can take a long-term view of things and really are looking ahead to see what the next disruption is. I mean, we're all talking about generative AI now. The next one after that, I think, will be quantum in terms of the excitement and the investments. So to give you an example of what Xanadu and others are working on, we're working on next generation battery development. So what many people may not know is pretty much all the major car companies out there have small quantum computing teams. So what they're thinking is once a quantum computer is powerful enough, 1 million qubits and so forth, what do we do with that size machine and how do we leverage it to develop new materials? As I mentioned before, like drugs is one, but materials is really, quantum chemistry applications are really the first focal point of what you can do with 1 million qubits. And so they're getting ahead of that. In our last round, we had Volkswagen put in $10 million of a $100 million round. And we work with them, we've got co-patents. And let's assume a few companies, I don't think it'll be a winner takes all, it'll be many companies, hopefully Xanadu, that can really get to 1 million qubits. But it won't be just one company. I think there'll be a few different approaches that can actually excel and start getting all these customers. Once a few companies get 1 million, then the barriers of entry, it's already quantum, the barriers of entry are already too high.
So if I run a whole bunch of simulations, how much better can my battery get?
Yeah, so the better that we focus on...
And what are they trying? What are the tests?
So we're not at that point yet. It's really more pen and paper and quantum computers and traditional machines. Like the thought experiment is assume we have 1 million qubits. How does that change what you do in the discovery of material simulations using, as you said, simulators? So let's assume what quantum algorithms can we use? And the key thing there is patenting now is really key. Because we just don't want to offer cloud compute service, no matter how much we charge. We want to be kind of the next AWS, but quantum. But imagine if our compute is actually used to create new drugs or new materials.
AWS quantum, so your business model is going to be, we make these quantum computers, you can rent space on them.
Exactly right.
And we'll load balance how much you use them.
Yeah, AWS is a good example. And also this unique thing too, where if we can, which we're doing, patent these things, we don't want a company to generate a new battery or drug and make billions off it, and they've used just our cloud compute time. We want actually to get the IP now, so we get licensing from using a new drug or a battery. So that's really key for our future revenue model as well.
What are the biggest surprises you've run into as you've built this business?
That quantum computing is hard, and it was always hard. But sometimes you got to stop and think. Like this is just as hard as say SpaceX or something that's changing our world and is very inspiring. It's kind of the other end of the spectrum. They're sending things to space. We're working on the quantum world. It's a very orthogonal sort of spheres. But this is probably one of the most complicated things, like far more difficult than the space program. To be fair, we're leveraging compute, we're leveraging technologies that have gone before us, so it's not like starting from zero. But this is hard. Like, And you know, the scalability side is hard, but having a photonic-based approach is really good. The other thing I didn't mention too is that you know, this footprint of half a football field, an acre of land that we have quantum computers, the quantum data center. For us, our approach, only 10% has cooling. And I think, you know, when we showed you that, we have some cooling, but when we said our computer operates at room temperature, the measurements, the gates, literally at room temperature, you know, it doesn't mean it's cooled down using some other approach. It literally means at room temperature. It looks like a normal server rack.
Yeah, that's a huge feature for you.
It is, and just from the fact that you can condense things, miniaturize things faster, but also the fact that, say, if you take a cryostat approach, you've got the chip at the bottom and the chandelier thing that everyone sees. It takes a day or two to cool it down. You've got the chip in there, you run whatever you want to do with the chip, and a day or two to heat it back up again. So you've lost up to 4 days. Whereas for us, you take the chip out and put it in. It's literally a minute or two to do that. So it's a race to 1 million qubits, and we like our chances because of, you know, one of those reasons.
Yeah. I mean, as I remember it, the optics can also be in an optical quantum computer can be in a smaller footprint too.
Yeah.
You don't have to have the big super collider or
Yeah.
the super cooling.
The cooling,
light.
that's right. Yeah, so the footprint will be much lower. And another thing that we didn't talk about is, you know, if and when quantum computing takes off, like the traditional chip industry, you're going to want to mass produce these things. So you're going to want to have tier 1 foundries that are actually pumping out wafers and chips. What's really great about photonics in general, is we can go to TSMC, we can go to global foundries that make our laptops,
sure.
The chips in our laptops. We actually have worked with global foundries. And the reason is that they can take our chip designs, because the telecommunication industry, they've been serving the telecommunication industry. So other approaches, which have great things about them too, you can't go to TSMC and say, hey, we have an ion trap chip or superconducting chip. They just don't have the tools for it. And as we've seen, like ASML and others, these tools cost like $200 or $300 million. There's also a backlog on this. So I think that's a huge benefit for our approach as well.
You've got, when you say quantum computing is hard, it's because you're working with the very, very small, right?
Exactly.
You're working with, you know, things at the atomic level.
Yeah, that's right. And
and things act weirdly down there.
Yeah, very weirdly. So if I had a tennis ball and threw it, the dynamics or how it evolves over time, we're not shocked by it. We've seen it since we're kids, very much our world. But we weren't born in a quantum world. That's why I was reading a book the other day. In 1900, a lot of scientists didn't believe that atoms existed. Like, that blows my mind every time I think of that. Just over 120 years ago, they didn't believe in atoms. They needed evidence and really forward-thinking people. And then, let alone quantum computing, quantum physics, which was really invented from 1901 or so to mid-1920s. Like, that's not that long ago. So 100 years ago, it was kind of finished. Not really finished because we're still discovering stuff, but the main foundation was developed, you know, less than 100 years ago. That blows my mind. And now we're trying to build computers out of it. I mean, just the ability now to actually leverage single photons or single atoms or electrons and manipulate them in a way that you can do computing, it's fantastic.
So is the problem that our models are very clear, like there's your proton, there's your electron, there's your neutron, this is what it looks like in theory, but then in practice, you basically got a proton with a plasma shell that is like, it's like a lightning storm around it.
Yeah, there's the...
is that the problem that we, like, theoretically this seemed like it was gonna be really easy to do, and now it's like, in practice, these are the things that are happening.
Yeah, for us, that manifests in, so we're using light, we have optical components, we have fiber optics. If you think of it like a communication channel, you send light from one end of the fiber optics to the other. Loss happens, meaning loss of information. Right. And so some of the light gets absorbed in the fiber optics, some of it gets scattered. That happens on chips the size of our thumbnail. And so our biggest challenge is loss. Now, when you have too much loss...
So you have loss information, not just a loss of energy. Or
Both, that's right.
Both.
That's right, because this
Can't you create longer wavelengths or?
the wavelengths we work at is telecommunications, so 1550 nanometers, and that's really key because a lot of the low loss components like lasers, fiber optics, they're really well engineered at that wavelength. So that's important. It also becomes a lot cheaper too because it's at the telecommunication wavelength as well. But no, loss also was a problem. We have fiber optics over Atlantic Ocean. We have it under our cities, and that's how we stream movies and have video calls. But it's perfect. It's a communication channel at very little error. And the reason is every kilometer, traditionally, you can boost the signal. So if you've lost information, you can boost it, and it's like, looks better, just as good as it was before. Quantum mechanically, the same principle of boosting actually adds more noise to it. So you're kind of screwed. So you need better ways and more, ingenuity to get over that.
But you have a shorter distance. You're not going across.
I know, and that's the best example to sort of show why quantum computing is so hard. Even at those, we're at distances literally centimeters, and it still screws up. And so that's why it's like, we're not even going kilometers, and it makes it hard already.
And the customers who are buying these things, are they helping you where they say, hey, we need this for this application. You've made it work for this other application, but why isn't it working for ours?
Hopefully,
does that sort of thing happen?
Hopefully that'll happen in the coming years, but at the moment it's still just understanding how you can connect the math of quantum physics with the math of simulations, batteries and so forth. So, it looks actually we're out of time.
We're out of time.
That was quick.
All right. All right, let's hear it for Christian Weedbrook.